Okay, so starting again here. This is 4. 4 also has water cycle, and that I separated out into its own unique PowerPoint. All right. So this kind of picks up on when we were talking about the food chains and the food web. All right, which is why it comes actually after chapter 3. But I wanted to continue kind of talking in the chain that we were in before and talk more about the physical aspects of the ecosystem. So that's why we went to 5 first. So now we're going to touch base before we move on and just kind of show you what was underlying, laying the groundwork for this stuff on the chemical aspects of things. So that's what we're going back in now and telling you what's actually being moved around and so on and so forth. I like some of the stuff that those 2 first videos were talking about. I don't, strangely, and even with my geology background, it's even stranger, I guess, that I don't mention it. I don't talk about the rocks in the earth so much. I kind of just, well, you'll see how I keep it. That is a component I can definitely add. But yeah, I mean, we're going to mention it here on this first slide, but I don't do it anywhere near as much as I could, I guess. So while we're looking at the bunny eating grass and the fox eating the bunny and I guess nobody eats a fox, but you get where I'm going there. You understood that we moved from a primary consumer. Well, we moved from a producer to a primary consumer to a secondary, and oftentimes a tertiary consumer. All right, and you got that idea. Energy from the sun transferred. But now we're going back down and saying, okay, what were we actually moving around? What chemicals were actually being ingested? What chemicals were actually being pooped out or peed out? Or when the critter dies, again, that upside down cow was kind of silly. What is going back where and how are we using it? All right, that's what we're going to get into now. So biogeochemical, again, biological, geological, and chemical. Just string all those words together and make a new one. Biogeochemistry is, in fact, a class that can be taken. Junior, senior level stuff. So, y'all got 5 cycles that you're going to be held responsible for. Carbon cycle, nitrogen cycle, phosphorus cycle, sulfur cycle. I guess I do talk about the sulfur cycle. I said a little while ago I wasn't sure. And the water cycle. And as I said, we single the water cycle out, give it its own PowerPoint. I had heard the schnapps before. I forgot all about it until now. The first video guy, I think, mentioned the schnapps. And as long as you don't spell it the way you spell peach schnapps, you probably will remember something, maybe. I don't ever ask you for a list, okay? But, again, should you go on in your environmental studies, maybe find yourself at SUNY ESF or John Fisher or something like that, it'll be helpful. So the carbon cycle. Obviously, we're talking about the movement of carbon. It goes between the oceans, the atmosphere, organisms, and rocks. All right, so this involves pretty much everything there is to involve. All right, and that's one of the aspects they talked about, where we find these various nutrients at. So we got photosynthesis going on in the background. We've already discussed photosynthesis. All right. The plants are taking CO2 from the atmosphere. So there's carbon coming out of the atmosphere. That carbon happens to be attached to oxygen, but that's okay. It works out. then through all the organisms that exhale. Plants exhale, but they exhale oxygen, so we're talking about everything else now. CO2 is returned to the, really should say the atmosphere instead of the environment here, but maybe put an atmosphere in parentheses there, because that really is exhaling. So I've always used the word carbon sinks. She used, one of the videos talked about reservoirs. And for some reason I don't list it on here. But the ocean is a really, really, really big carbon sink. Easiest one to think of, though, are the forests. And this is one of the reasons that clear cutting, all right, just taking down huge swaths of forest at a time, it's like a triple banger of bad, all right? So there's a lot of carbon stored in the trees. We just talked about that through photosynthesis, right? And then once you cut them down, well, what do? Well, typically you slash and burn, right? Sometimes they take some of the wood, but a lot of it is just burned. Well, that returns that carbon right back into the atmosphere. And then I said this was triple bad. Why? Well, kind of goes without saying maybe, but at this point I will. They're no longer there to absorb any more carbon. Okay? So not only did you release all the carbon that they've been storing for hundreds of years, but they're gone and they no longer will be able to store any more of that carbon. Maybe again, this is one of the common themes we have, that nature finds an equilibrium. As much as we try to pump out, the plants do their job, suck in what they can, but when you start erasing the plants, you really mess with that equilibrium. Fossil fuels, again, is another huge storage place. You're well aware, okay, about coal. You hear, you can't really go very far without hearing about the evils of coal. But even oil and gas, okay, not great with regards to releasing carbon once they're combusted. All right. Again, coal's really easy to see because, pretty much everybody knows that coal is old plants. But oil, okay, those organisms as well. Sometimes plants, sometimes animals, sometimes a little of both. They call them fossil fuels, but somehow you just don't always make that connection. So that carbon, again, is returned. So see, it says right there then, the combustion returns this carbon to the environment. The carbon is oxidized. Remember, oxidation means adding oxygen into it. So it's turned into CO2. And then we also get some, why do I mention water, heat, and light? The water I can understand, but the heat and light, I think I'm probably going with that conservation of energy, conservation of mass here, that when you literally combust, you are creating more types of energy than just you're creating energy, you're releasing energy, I guess is the word I want to say, in addition to the carbon. Yeah, I'm not sure why those two last things are there. The carbon silicate cycle. So this is a little bit of geo going on here. You hear a lot about acid rain, and when you hear about acid rain, typically they go straight to sulfur, sulfuric acid. And I think that because that's just really scary. The average person doesn't know a whole hell of a lot about acids, but they do know sulfuric acid. Oh my God, that's horrible. We don't want that falling. I think that's almost a marketing thing, that's like the first thing you hear about. Now, don't get me wrong. There's plenty of sulfur in coal, and it is truly happening, okay? But I think that's sort of the poster child for it, because sulfuric acid just immediately, you know, goes off in somebody's head. But carbonic acid is out there just as much. And when the carbonic acid hits the earth, you guys probably don't know this unless you took geology. All right, silicates are everywhere. They're like the most commonly occurring mineral group at the surface of the earth. Many rocks contain silicate stuff. All right, and calcium is quite frequently bonded into that mix. So the calcium is released into the oceans, used to make seashells. All right. There's a whole other process going on there. And those seashells eventually form limestone, which it isn't in here. I didn't actually go so far. Yeah, there's not another page for this conversation. The seashells are made out of something called calcite, which is calcium carbonate. So they pull in the carbon, it's actually CO3 at that point, out of the oceans. It's another reason we want carbon in our oceans, so we can have all our seashell critters. At any rate, and then when those guys die, they form a nice little sludge, and hundreds and thousands of years later, that turns into limestone, and it might get exposed to the surface. And when it gets exposed at the surface, well, you've heard of weathering and erosion, right? And that breaks down and returns the carbon dioxide to the atmosphere. Now, as one of the guys in one of those first two videos said, this is a pretty long process. This is a whole heck of a lot longer than eating plants, eating the critter that ate the plants, so on and so forth. All right. But it is definitely there, and it is pretty independent of anything else that's going on. So this is something Mother Nature's, just doing herself in the background. And it's pretty neat. Pretty neat. Seashell, not to go back to evolution, but the appearance of seashells in the fossil record, the appearance of seashells in life, all right, about 550 million years ago or so, I think it's 540 actually, is a huge step in allowing life to be more and more complex. Seashells were like the first skeletons. Skeletons, for us, provide not just sites for muscle attachment, but they also provide some protection for the organs. Think about your rib cage and so on and so forth. So we've been able to do so many things. Think of all the different kinds of animals that have skeletons. All right. Well, there's a lot of invertebrates out there, right? Things without skeletons. And the seashell was really the first way that they managed to do that. And again, that just allowed an explosion of diversity that wouldn't have been possible really without the carbon cycle. So when I said that this occurs, independent of stuff that we're doing, yeah, we affect it, but Mother Nature's been doing this forever. Absolutely ever. So, neat stuff. And this is the textbook's wonderful drawings. Now you're getting used to these with all their arrows pointing everywhere and the way too many critters. This one's actually fairly tame compared to some of those food web ones we saw. I would start in the air if I were trying to understand this or process this mentally. All right. And let's pull the carbon dioxide out of the air and into one of the many pathways that we talked about. And then once it's down on the Earth itself, you see a handful of trails, pathways that it could take. Some storage, some usage. And then how eventually, the only thing I don't see on here, oh, there it is, combustion. I'd say the only thing I don't see on here is a power plant or something like that, but there's the city buried in the background there. And then the respiration, the exhaling that we talked about. I'm not sure what these numbers are and why they're only in certain things. I don't know if it's parts per thousand or what they're doing, and I do not see a key on here anywhere. Could be percent. It's not percent, obviously, because we have 38,000 over there. So, yeah, I'm not sure what they're doing with these numbers here. We're just going to ignore the numbers. But the general flow of things is pretty all right. So this is one that we have been messing with for a couple hundred years. You guys have had history way more recently than I have. When was the Industrial Revolution? Is that the 18s or the 17s? 17s? Okay. So the last 200 to 300 years, we have been pumping carbon in way greater volumes than Mother Nature herself was doing. All right, and as I always talk about, nature tries to achieve an equilibrium. Well, we're outside of nature. I've said that before. I'll say it again. Sometimes she brings us back in, something fierce, right? But nothing like a big storm or an earthquake or something to remind us that we are indeed in nature. But for most of our everyday goings-ons, we're kind of out of that little cycle. And but boy, do we contribute to it. We talked about fossil fuels. We talked about deforestation. And again, what that does is remove the carbon from these natural sinks, these natural storage units, and puts it back into the air. And of course, that has to have some effect. And it's typically not Mother Nature has to work faster to try and keep up with us. That part doesn't really work. That thought process doesn't really work. So, how we were measuring atmospheric CO2 in the 1700s, I don't know. No, actually, I do know. All we have to do is look at ice cores. Okay, it's very easy if you go to the right places to find ice that's a couple hundred years old, and ice always has air bubbles in it. Okay, we could find thousands of year old ice. That's how they'll go, and they'll tell you, oh, during the last ice age, the composition of the atmosphere was this. We have these cool little capsules, time capsules, full of air. All right, so anywho, you see the percentage there, and oh my gosh, it went up. And now, I think we've had this conversation here. You look at that number, you're like, oh, that's so small. That can't hardly matter, right? And I don't even mean the increase. I mean the actual number itself. We're used to say, someone says, oh, I'm going to tax that % of your salary, or, you'll miss this many points. You say, that's such a small percentage, I can't even be bothered to worry about it. That's how we're used to thinking about this stuff. But when we're talking about, again, out in nature, when we're talking about % composition of something, especially something that has such a huge effect as atmospheric composition, what we have is a function of that composition. So at that incredibly small number of 0.038, okay, we have the weather that we have. We have the climates that we have, the ecosystems that we have, whatever you want to say. When we change it, well, that's going to change all of that other stuff too. Okay, it's a small number. We still can't ignore it, I guess is my point. And moving up to 0.06 is a lot. All right? It really is, even though that's really, 600s, it's not a big number, comparatively speaking. So I won't beat that into the ground, but just that does happen. And I think we've said this as well before, not all greenhouse gases are created equal, okay? There's lots of greenhouse gases, and everybody, again, when the senators, not to pick on the senators and the Congress folk, but, when they want to lead you down a path of don't worry about carbon dioxide, for example, they'll point out, well, water vapor is a greenhouse gas. And all the water vapor that's out there, you want us to get rid of water vapor? Good luck. Da, 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 da. And then now you're worried about water vapor and you've forgotten about carbon dioxide, right? But water vapor and carbon dioxide are not equal in their heat trapping abilities, okay? Carbon dioxide is significantly eviler or more powerful. So, it is a problem. All right, and it is a problem, and believe me, I am not going to give up my car and start taking the bus everywhere. I get it, We got to figure something out, though. Okay, we got to figure something out. We need to figure something out. You're not going to fuel power Manhattan on solar panels and windmills. It's not going to happen. All right, at least not for a while. So we are tied. We're stuck in this carbon loop. Okay, we just need to figure out how to make it a little better. So, and at any rate, as we said here, you see another bullet point. And I already mentioned this. We can go back. We can see this. And again, the way they see this is when they're pulling out these ice cores, whether you're in Antarctica. You don't even have to go to somewhere as extreme as Antarctica. But that's typically, where they'll show you this stuff. And you pull out these ice cores, and sometimes they could be hundreds of feet long, and it's literally a chronology, okay? And you could count it kind of like tree rings. Now that stuff's starting to melt, the top of the chronology is getting a little blurred together. But when you go down pretty deep, where it's still very, 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 very cold, you can tell the layers. You can count back years. So, and like I said, we can see back to the ice ages, and that's again where we know things like CO2 is a huge driver of climate, because when we were in the last ice age, CO2 levels were very low. I don't know the percentage off the top of my head. When we melted out of those, CO2 levels were higher. All right, so they're not making this crap up. They really, really aren't. All right, so I talked about carbon not just because of its importance, but because it's something that out of all these you guys are probably most familiar with. This next one, the nitrogen cycle, all right, it is important. If any of you are farmers, you possibly is something you have to be cognizant of. All right, I don't know how many folks around here have fields to tend, but over the years I've had some. I lived in the Midwest for many years, and they're very agricultural out there. They mentioned in the video, again, that we have figured out how to break up our own nitrogen. You'll see, and I'll probably end today on nitrogen cycle because there's a lot of nooks and crannies in this conversation. You'll see that it does happen just fine in nature, but not to the levels that we needed to grow the kind of food that we want to grow. and where we want to grow it, and so on and so forth. Why do we care about nitrogen? Again, it's important building block. All right. And way back when we talked about the composition of the atmosphere, we mentioned that nitrogen was number one, but it more or less just sort of passed through us inertly. And we didn't say too much more about it. We maybe mentioned the bends. And otherwise, nitrogen didn't really affect you in any manner atmospherically. All right. And maybe in a large part that is due to the fact that it was N2. You know, I don't know if things would go a little differently if you somehow inhaled N's instead of N2s, but for the most part, it just passes through us inertly. However, at other levels of life, it's quite crazy. Sorry, my watch has been literally dinging for the last 3 minutes. I don't know what's going on, but I don't think I'm missing anything horribly important I have to look at. 5 steps. Tell you, you need to remember them in order. Okay, that's the one thing. Got to remember these in order. Please and thank you. And it's one of those annoying questions where they're going to be jumbled. One will be alphabetical, one will be reverse alphabetical, a couple will be mixed up. I'm sorry, but I am giving you 3 weeks' notice. Remember it. And then, of course, you'll be responsible for knowing what these stages actually are. Okay, nitrogen cycle is pretty important. So fixation, nitrification, assimilation, ammonification, and denitrification. These are primarily bacterial processes. Another reason, I suppose, we don't want antibiotics all over the dang place like they are. Don't get me wrong, I love my hand sanitizer. And when I go to the doctors and I'm not feeling well, especially in the winter, the first thing I want, why don't you give me an antibiotic? Ooh, they're overprescribed, but you know, we always hear that. It's true, though. Okay? It really is true. The sprays that you have for your kitchen counters, your bathrooms. We need bacteria around us. All right? It's important. Some of it is harmful, but by far it's outweighed by the good stuff. Okay, so the first step is fixation. I told you, loosely speaking, the other day that fixing is eating. Fixing is making something usable. All right, there's another use of fixing that's what I was talking about. In this conversation, it means making something useful. So we're taking that N2 and we're turning it into ammonia. Now, here's another thing that's going to annoy you guys. There's ammonia, there's ammonium, and I think there's another one too. Do your best. Again, I realize this is confusing, so I try to be as forgiving as possible when I'm writing the questions. So this can be done both in the abiotic realm and the biotic realm. All right. We already mentioned the bacteria, of course, but just in everyday life, combustion can break up nitrogen, fire. Volcanism, I'm not really sure how volcanism does it. Maybe extreme heat. And then the lightning striking through as it goes through the air molecules. All right. Splits all those little ends right in half. So the first step is breaking that nitrogen in half. Excuse me. And turning it into, adding some hydrogens to it, forgive me, and turning it into ammonia, which is NH3. Okay, 3 hydrogens. Plenty of hydrogen around as well, by the way. Okay, now nitrification. We're taking that ammonia that we just made. Let's stay in the bacterial realm. Let's not worry about volcanoes and lightning right now. Okay, so we're taking the ammonia and turning it into NO3. No, that's not nitrous oxide. It's like nitrous oxide? Oxide? No, it's the same one I just said. It isn't. Chemistry was not my fan. I was not a fan of chemistry going through this. But they have different endings. And some of you who are great in chemistry know this, depending on whether there's 2 O's, 3 O's. Okay. And this, again, this is back, well, it's nitrate. There you go. It's right there at the bottom. So NO3 is nitrate. And it's worth noting that this also can happen with NH4, not just NH3, ammonium. And that is, got a chemist wandering through the hallway there. She's probably shaking her head at me. That is one of the ones that we see in some of our cleaning products as well. So again, just to reiterate, since I stumbled a little bit there, all right. First of all, we're taking the atmospheric nitrogen, and we are blending it with some hydrogens to make ammonia. Nitrogen to ammonia, first step. Kabish? All right, and we call that fixation. Then we take that ammonia and we turn it into nitrate. Second step, called nitrification. Okay? Again, working with the bacteria line here. Assimilation, bringing it in, sucking it in, however you want to say it. Trying to decide if there's trouble in the hallways there. I think we're okay. So the plant roots absorb the nitrates that we just made. It's also worth pointing out, if only to confuse you, that they could have used that ammonia and that ammonium as well. All right, but they really like the nitrates. Really like the nitrates. So that goes into the plants as food. And then when the critters eat the plants, well, they use that to build proteins. We're skipping a lot if you hadn't noticed, which if you'd like me to get into how we build proteins out of nitrogens, I hope you don't. But, okay. So we're staying in this little realm here. And again, I'm not taking it past that. The textbook will try to explain to you guys a little bit more of what's going on here. I have distilled this a lot. But it's really not, in my mind, necessary in the realm of this class. We're giving you a loose outline as to how nitrogen moves through the systems. All right, urea. Everybody loves urea. All right, so the nitrogen-containing waste products, again, how do we get that? Well, that's all your bodily functions going on there, the extractions and your kidneys doing this and that and so on and so forth. That is excreted, all right? Everybody else except us just pees in the woods. Occasionally we do, but normally we don't. So again, that is, if you want to talk about unbalancing cycles, right? If you're out in the woods and your squirrels and your bunnies and your whatever, you generally don't travel very far. So the food you're eating, that from the bacteria that's there, that this nitrogen stays very, very, very local. However, when we're eating strawberries from Chile, tomatoes from Bangladesh, and whatever else from another part of the world, and then we put them into the water treatment center, it's really messing things up. Now, if you bring in the idea that, okay, more than likely we used artificial fertilizer to grow those, that's a whole other conversation. But let's say you're good. Let's say you try to eat local. All right, you go to the farm store as much as you can when they're open, and you buy only local stuff that they've grown or somebody nearby has grown for them, again, unless you've got an outhouse out back, you're still not returning any of those nutrients into the local area. And I'm not suggesting that you do, okay? I don't want you all going out and start peeing behind your house and everything like that just to keep things crunchy nutty. But I'm just pointing out that, what the hell is he talking about? Just pointing out that, you know, this works a lot better in nature than it does here, okay, in humans. Again, this is why I'm constantly arguing that we're sort of out of nature, out of these cycles. Don't use that as license to act however you want, okay? But, anywho. So, ammonification, that is the body processing it out. Again, the bacteria, I'm going to use that and create ammonia or ammonium. And that's actually possibly what's going on. I don't know that much about water treatment. I'm pretty sure there are some bacterial levels to water treatment. You guys go to the recycling plant. I don't know why we never arranged a tour. There's a water treatment plant right before there. It's not the nicest smelling place. That might be why. But there's that solid waste, and pretty sure they do water treatment down there as well. So we go back in at the nitrification level. Just a reminder. You're going right back to step 2. Okay, at the ammonification. You go back to nitrification. I'm sure we have a wonderful graphic about this soon. Denitrification. Now we're working with the nitrate, the NO3 again. The bacteria break that down and release nitrogen again. If you're wondering what the bacteria are doing in here, they're utilizing the energy, okay, is what it boils down to. Bacteria eat an amazing amount of things, and that's quite possibly why they're so diverse, okay? They've adapted over the millennia to just survive on just about anything. So the ones down at the deep sea vents, you may have heard me talk about that. Okay, they eat sulfur. Okay, hydrogen sulfur comes out of the ocean vents, and there's critters there. They're the base of the food chain. They eat sulfur. So bacteria are just crazy, wonderful things. So that puts the nitrogen back into the air, so it could be, again, through this process. And that, my friends, is the nitrogen cycle. Okay, it's not, I'll say, horribly complex. It's pretty straightforward, especially if you make just like a little story paragraph out of it. But what's scary about it for a lot of folks is the amount of vocabulary words, okay, that all start with nitra. That's the hard part. So give this a couple minutes when you are getting ready to start studying. Again, I'll look as we get closer to test time, you know, just how much of this is on there. But I guarantee you there's a couple questions about, you know, what these steps are. So how do we interact with all of this? Well, again, mostly fertilizers. And I talked about most of this already. Once we figured out, I didn't realize, you know, I guess artificial fertilizer would be a huge product because, you know, cow poop and chicken poop and pig poop, so on and so forth, is plentiful. Don't get me wrong, but it's not great to ship, and I'm guessing we've figured out how to tinker with, you know, the good parts of that, so to speak, that the plants actually want, right, and get rid of maybe the stuff that we don't want. And I suppose somewhere deep down inside, people probably feel better putting some random chemicals on their plants than they would, you know, shoveling poop onto their plants. I don't know. I don't know. I think it's probably more a supply and demand thing, you know, than anything else. But so fertilizers. We talked about the algal blooms already. So that's what it does. And again, that not just keeps you out of the lake, that could end up killing the organisms in the lake because the algae, they have a huge influx of food, but they need other things, okay? And that's not a sustainable level. So they inevitably die, and then other organisms start to break them down. It's a mess. All right, so again, here's our nice little summary. I see they took the smog off of the city now since we're not talking about carbon. That's nice. We're going to start again in the atmosphere. We're going mostly to the left here this time, it looks, counterclockwise. I don't know if that was the case in the previous one. I think they had arrows going every direction back there. But now we're going counterclockwise here. Going right through the hawk plays no part in this, I don't think. Down through the soils. That's where the majority of this takes place, in the soils. Into the farmlands. Back into the water, some of it. And then from the animals, their waste, be it the pee, typically, but even sometimes the poo, goes back into the soil where the bacteria denitrify it and return it back to the atmosphere. All right, so we're not going to go to the phosphorus cycle right now, as I said, but perhaps now you can also see why I felt the need to liven this up a little bit. We will go back and finish this and then move on to the water cycle, which is a good bit more interesting. I actually have a really good Blue's Clues episode that talks about the water cycle. I probably won't show you that one, though. But you could find it out there. It's called Stormy Weather. And they do an amazing job teaching 2-year-olds all the parts of the water cycle, or however old you were when you watched Blue's Clues. I'd still watch it if it was on, but I like the originals, like Joe and Steve. Steve's the best. But all right.